Earth's hot body.
Let's take a look at Earth's structure and find out what makes it so, well, hot.
We'll discuss two different ways of categorizing Earth's structure. First, we'll discuss how Earth is composed of a core, a mantle, and a crust. Then we'll look at the planet's physical layers: the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core.
Just remember, the center of the Earth is hot. In fact, the center of the Earth is as hot as the surface of the sun.
You're as hot as the surface of the sun.
Why, thank you.
The core, the mantle, and the crust.
The Earth has a hard core. It also has a hot, sludgy mantle and a solid, thin crust. Let's start by looking at Earth's core.
The Earth's core is a liquid metal ball at the center of the planet. The very center, called the inner core, is solid metal. The core is made mostly of iron. That means it's extremely dense, making up a third of Earth's mass. This layer outside the core is called the mantle. It's the middle layer of the planet, and it contains most of Earth's mass. The mantle is made mostly of a super dense, slow-moving liquid rock, although the upper layer of the mantle is brittle.
The crust is the outer layer of the Earth. The crust is the thinnest and lightest layer of the Earth. It's the part we humans are the most familiar with.
There are two types of crust: continental crust and oceanic crust. The continents are made of continental crust. The ocean floor is made of oceanic crust.
Duh!
Think of continental crust like a lovely thin crust pizza. Oceanic crust, on the other hand, is like a thick, doughy French bread pizza. Write that down, and someone get me some Parmesan.
We've been talking a lot about density, haven't we? That's because the structure of the planet and the way Earth's layers are arranged has everything to do with density.
Thank you for calling the Earth Science Hotline. What can I help you with today?
Well, I never admitted this to anyone, but the truth is that I don't have a clue what density is.
Shh, it's really not so bad. Just think of density as how much mass an object has per unit of volume. You know how much stuff you have in a given amount of space. You're all right.
Take this wad of cotton, for example. It's super fluffy. Now watch what happens when it gets all scrunched up together. It still has the same mass, but it has a higher density than before. That's because it's the same amount of mass stuffed into a smaller amount of space.
Earth's layers are organized by degrees of density. Things that are less dense float on top of things that are more dense. That's why the solid metal core lies at the center of the planet, followed by the sludgy mantle, and finally the light, thin crust.
So what determines a thing's density? What it's made of course. You know, its composition.
Both the crust and the mantle are composed of mostly oxygen and silicon. But the mantle is denser than the crust because it also contains magnesium. That's why the crust floats on top of the mantle, because it is less dense. And of course, the iron core is the densest of all.
Earth's composition all goes back to its days as a cooling planet. Gosh, I remember those days. After Earth's fiery beginnings, all the densest materials gathered to the center of the planet as a result of gravity. That's how it got an iron core. The outer layer of the mantle cooled and hardened and became the crust, while the stuff below it remained hot and gooey, and the rest is history.
It's just like that episode of Nicole and Herman when Herman made a molten chocolate cake and Nicole didn't know the inside was all melted chocolate until she took a bite out of it. It was so funny.
Let's review. Woo! Dividing the planet into the core, the mantle, and the crust is a way of dividing the planet into layers based on what they're made of, like iron, magnesium, and silicon. Woo. Woo.
Now we're going to look at a way of dividing the Earth into layers based on how each layer physically behaves, like whether it's solid or liquid. It's not a better or worse way of categorizing, it's just different. So grab a stuffed animal and let's go for it.
Earth's other layers.
This time we're dividing Earth into 5 layers: the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core.
Wait, what's wrong with the core, mantle, and crust? Are they outdated or something? Did I not get the memo? Gosh, I just can't keep up.
Calm down. You haven't missed anything. The core, mantle, and crust are not outdated. You see, scientists use both ways of categorizing for different purposes. That's all. Like we said, the layers we're discussing now divide the Earth based on physical properties, such as liquid or solid.
The lithosphere is the outermost layer of the Earth. It consists of the crust and the upper part of the mantle. These parts are both rigid. The lithosphere is Earth's rigid outer layer.
Beneath the lithosphere comes the asthenosphere. The asthenosphere consists of the middle portion of the mantle. This area is extremely dense.
Not even. It's extremely, extremely, extremely dense. Even if it weren't insanely hot, you wouldn't be able to go swimming in the asthenosphere. It's too thick. Think of it like a liquid that moves so slowly it's nearly solid. Or you can think of it like a solid that is ever so slightly melted.
Next, we have the mesosphere. This is the part of the mantle between the asthenosphere and the core. The mesosphere is denser and more rigid than the asthenosphere. It makes up the largest percentage of the mantle.
Now remember how we said the Earth's core is made of solid metal? Well, that's true of the inner core, the very center of the Earth. However, the core's outer layer is actually liquid. This liquid outer layer makes up the bulk of the core.
So there you have it, Earth's other layers. The lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. Shall we think of a silly way to remember this?
How about lost ants march over ice? Let's try it. Lithosphere, asthenosphere, mesosphere, outer core, and inner core. Brilliant!
Ah, yes. Lost Ants March Over Ice. It was the name of my band back in college. I can still picture us now. Nothing more but 3 strapping lads, 2 bagpipes, 1 triangle in the wide open road.
Evidence from inside the Earth. So wait, I have a question. Has anyone ever been to the inside of the Earth?
Well, I heard there was this one guy from New Jersey.
No. The answer is no, absolutely not. That would take a lot of digging, and not to mention you'd be burned to a crisp.
So then how does anyone know what it's like down there?
Elementary. Just because we can't go to the inside of the Earth doesn't mean we can't gather clues and evidence about what it's like in there.
There are a few places scientists can look for clues to what's going on deep inside the planet. For example, sometimes stuff from the mantle oozes up to the surface through openings in the crust. You know, like a volcano.
You ooze up to the surface through openings in the crust. When this happens, it allows scientists to study material from the mantle and figure out its composition.
Another clue to Earth's interior is its magnetic field. That's right, you heard me. Earth has a magnetic field. You heard it here first.
Just like a magnet, the Earth has a north and a south pole. These create lines of magnetic force that loop from one pole to the other. That's Earth's magnetic field.
The planet's magnetic poles are not exactly the same as its geographic poles. They're tilted about 11 degrees away from each other.
Scientists believe that Earth's magnetic field is the result of the movement of a liquid iron in the outer core. When the liquid metal moves, it generates an electric current that produces the magnetic field. Far out.
You see, there's always a paper trail. I mean a magma trail. I mean a magnetic trail. Well, whatever. We're hot on it.
Shifting Earth.
Have you ever wondered what a world map would look like a billion years from now? What if Asia and North America joined as one giant continent? Is this even possible? Well, we're about to find out.
Before we start, there's a few things you should know. First of all, Earth is dynamic. Dynamic means that Earth shifts and moves around a lot. In fact, Earth is constantly changing.
Second of all, Earth's crust is not one solid piece. It's made of many pieces that fit together like a jigsaw puzzle.
These pieces are called tectonic plates. And you know what? Tectonic plates move. The theory of how and why they move is called plate tectonics. Let's go there.
Plate tectonics.
So what exactly are tectonic plates?
Tectonic plates are pieces of the lithosphere, that rigid outermost layer of the Earth.
Because they are lighter, they float on top of the dense asthenosphere.
Earth's surface is covered by 10 major tectonic plates, like 10 gigantic floating puzzle pieces. As you can see, most plates contain some continental and some oceanic crust. Others, like the Pacific plate, are all oceanic crust.
Think of tectonic plates like delicious graham crackers and marshmallows floating on top of hot chocolate fudge. The graham crackers and marshmallows float on the chocolate because they are less dense than it, just like tectonic plates float on top of the dense asthenosphere.
Now, these tectonic plates are not like islands floating way out there all by themselves. No. Like we said, they're more like puzzle pieces. That means they're all cozied up right next to each other. That means that sometimes they touch each other. You know? They interact.
So what exactly happens when two tectonic plates interact?
When two plates interact, they can either collide, separate, or slide past each other. What two plates will do when they interact is defined by the type of boundary between them. A boundary is just the place where two plates meet.
Where two plates collide, we call this a convergent boundary. The word converge means to come together. Really, it's just a nice way of saying collide.
So what happens when two plates converge?
It depends on whether the colliding edges of the plates in question are made of continental or oceanic crust. That's because oceanic crust is much denser than continental crust.
Picture a collision that occurs between one piece of light continental crust and one piece of dense oceanic crust. What do you think happens when the two collide?
Let's get back to our graham crackers and chocolate to figure this one out. And don't forget the marshmallows. Since marshmallows are less dense than graham crackers, we'll think of them like continental crust. And the graham crackers will be the denser oceanic crust.
Looks like those two are about to collide. What will happen? Oh, the graham cracker is sliding beneath the marshmallow. Look at it go!
When oceanic and continental crust collide, the denser oceanic crust tends to slide beneath the lighter continental crust, sinking into the asthenosphere below.
This type of convergent boundary gets its very own special name. It's called a subduction zone. When something subducts, it just means that it sinks. It may also stink. We just don't know.
Mountain chains are often the result of subduction zones occurring at the edges of continents. When the dense oceanic crust dives beneath the continental crust, it pushes crust upward to form a mountain. Ooh.
Convergent boundaries can also occur between two pieces of continental crust, or two pieces of oceanic crust.
When two pieces of continental crust collide, the two pieces buckle and push up against each other, causing the crust to rise upward. It may not surprise you to know that some of the highest mountains in the world are formed when two pieces of continental crust collide.
Finally, when two pieces of oceanic crust collide, one piece dives below the other, creating a subduction zone.
Let's review! Woohoo! Convergent boundaries are places where tectonic plates collide. But remember, tectonic plates can also pull away from each other or slide past each other. Let's take a look at these other types of plate boundaries.
When two tectonic plates move away from each other, this is called a divergent boundary.
Divergent boundaries occur most often on the seafloor when two pieces of oceanic crust are pushed apart from each other. This creates an opening in the crust. Through that opening, hot magma comes bubbling up. The magma quickly hardens and forms a sort of underwater mountain called a mid-ocean ridge.
Remember, to diverge just means to move apart. A divergent boundary is where two plates move apart.
The last type of plate boundary we'll talk about today is called a transform boundary. A transform boundary is where two tectonic plates slide past each other.
Well, slide isn't quite the word I would use. Tectonic plates aren't made of butter. They're made of rocky, jagged edges. When they rub past each other, they grind, jerk, and quake. Can you guess what we humans feel when tectonic plates slide past each other?
Oh, earthquake! Quick, honey, grab the tuna! The tuna, I said! No, the tuna! I'll forget it, it passed.
Evidence of plate tectonics.
There was once a time when people believed the Earth was flat. There was once a time when people believed the Earth was the center of the universe. There was once a time when people thought that penguins grew on trees. And there was once a time when people had no idea about plate tectonics.
Plate tectonics is the theory that the surface of the planet is divided into large plates like puzzle pieces. These solid pieces float atop the hot, liquid layer below them. They are constantly shifting around.
But scientists did not always know this. They used to believe that the surface of the Earth was completely static, that it didn't move or shift at all. What were they thinking?
Early in the 1900s, that belief was about to change. The scientific community was about to undergo a major shift of their own, having to do with their perception of the planet. That shift had a lot to do with one German scientist named Alfred Wegener.
He was a true detective, a role model for sleuths of all shapes and sizes. That man knew how to let the clues speak to him.
Alfred Wegener and the Case of Continental Drift.
Part 1. The Clues.
What clues did Alfred Wegener have that led him to the theory of plate tectonics?
Clue number 1. Fossils of identical plants and animals had been found on opposite sides of the Atlantic, and these were not animals that could swim.
How is that possible?
How is it possible?
How is it possible? It can't be!
Could it?
Clue number 2. The coastlines of Africa and South America had the uncanny appearance of being able to fit right together, like puzzle pieces.
Part 2. The Red Herring.
Scientists of the day hypothesized that sunken land bridges had once connected the continents, and that this explained the existence of identical fossils on different continents.
But Wegener was like, I don't think so. He couldn't deny the uncanny way the shapes of the continents seemed to fit together.
Part 3. The Solution.
Wegener became convinced that the continents were once joined together in a great landmass he called Pangaea. Over hundreds of millions of years, Pangaea split apart and its pieces have been drifting away ever since. These pieces are what we today know as the continents.
Pangaea is an example of a supercontinent, a mass of all the continents stuck together. These days, scientists have a lot of evidence indicating even older supercontinents that predate Pangaea. Take a look. Go take a look. Go now. Go take a look!
Scientists have pretty solid evidence for the existence of the supercontinents Rodinia, Panatia, and Aldredia. Less solid evidence indicates the existence of still older supercontinents, and some scientists have named what they believe to be the oldest supercontinent, Valbara. 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 Valbara.
Scientists even have hypotheses about what future supercontinents might look like. For example, some scientists believe that North America and Asia will eventually merge. Imagine that!
Keep in mind that these supercontinents move apart and come together over billions of years. Continental drift happens extremely slowly, so you would never actually see something like this happening.
So long, brother. May the sun be always on your nose.
Let's get back to Wegener's story, shall we? Wegener referred to his theory as the theory of continental drift. How did his peers in the scientific community react to it?
They hated it. They thought the idea that solid rock could move was ridiculous and that Wegener's theory was complete rubbish. Ouch.
Despite the poor reception, the truth is that Wegener had made great strides for science. He had gathered an unprecedented amount of evidence to support his theory.
Just imagine you're trying to put together a giant puzzle of the Earth, but the pieces are scattered helter-skelter all around the world. Wegener painstakingly combed the planet to find the pieces of the puzzle that fit together. Yes!
For example, he pointed out how the Appalachian Mountains of North America matched with the Scottish Highlands. That got him to thinking they had once been a part of the same range.
Pretty impressive. So why did no one believe the poor guy?
The problem was, Wegener was never able to properly explain why or how continental drift happens. He died before anyone had given his story much credit. The moral of this story is, if you're going to claim that solid rock can randomly move around, you'd better have a darn good explanation for it.
It wasn't until after his death that Wegener's theory of plate tectonics became widely accepted. What changed, you ask? Well, new evidence came to light and the case was reopened.
The evidence came from the ocean floor, from something called sea floor spreading.
Sea floor spreading happens when two tectonic plates pull away from each other. This causes a break in the Earth's crust that allows hot magma to bubble up from below. Once it reaches the surface, the magma piles up and hardens into new crust. This new crust forms a sort of underwater mountain called a mid-ocean ridge.
Each time new crust forms at a mid-ocean ridge, it pushes old crust farther and farther away. By observing that oceanic crust gets older and older the farther it is from a ridge, scientists gain solid evidence that Alfred Wegener's continental drift theory might actually hold water.
Now, you may be wondering, how do scientists know that a piece of crust is older or younger? Do they have psychic superpowers or something?
Nope, what they have is good old-fashioned evidence.
First of all, scientists could see that sedimentary layers became deeper the farther one got from the ridge. But that's not all. Eventually, they discovered even stronger, undeniable evidence of seafloor spreading. Check it out.
Earth has a magnetic field, right? That means it has a magnetic north and south pole. Now watch this. Every once in a while, the poles switch places. The North Pole becomes the South Pole, and the South Pole becomes the North Pole. This is called magnetic reversal.
It turns out magnetic reversal was the key to providing evidence for seafloor spreading. Here's why.
The magma bubbling up at those mid-ocean ridges contains tiny bits of iron. Those bits of iron are magnetic. Just like compasses, the pieces scurry to align themselves toward the north while the rock is still liquid.
Once the rock hardens, that's that. The iron is in its final resting place, facing north. But eventually another magnetic reversal occurs and the poles switch. When that happens, those old bits of iron become like a snapshot, forming a freeze frame of where north used to be.
So maybe you're wondering why. Why do magnetic reversals occur in the first place? What freakish reason could there possibly be for magnetic poles to randomly switch places?
Well, I was watching this thing on TV one night that said there's an alien spaceship at the center of the planet, and every time an alien flushes a toilet...
Whoa, whoa, whoa. Everyone knows that aliens don't use toilets. The truth is, scientists think magnetic reversals have to do with disturbances in the planet's liquid iron core.
So what's the point here? The point is that rock contains a historical record of magnetic reversals that scientists can observe. It tells scientists that they are looking back through time. It provides them with solid evidence of sea floor spreading.
All right, let me see if I can follow this rabbit hole back to its source. Magnetic reversal provides evidence of sea floor spreading. Sea floor spreading was the missing link in Alfred Wegener's theory of continental drift. And continental drift is evidence of the theory of plate tectonics. Earth's crust is not static, it's dynamic, it moves.
Stellar sleuthing. That's how you follow a trail all the way to solution. It's the Alfred Wegener way. Observation, instinct, evidence.
Phew! That is one hot trail of evidence. And guess what? We haven't reached the bottom of it just yet. That's right. Just like every good mystery, this one goes deeper still. And you know what? The deeper we go, the hotter it gets.
It's time to go straight to the very core of this mystery. Why is Earth so restless? What's driving all this dynamic motion? Does Earth have ants in its pants?
Close. Earth has heat in its core. That's why it can't stay still. The movements of Earth's crust are a direct result of the heat in the planet's core.
The truth is, Earth scientists haven't fully figured out the details of how exactly this works. But they do have some good theories. One theory of how heat from Earth's core drives plate tectonics involves a process called convection.
Convection.
Stuff that's hot rises, stuff that's cool sinks. That's convection in a nutshell.
But why does hot stuff rise and cool stuff sink?
Well, it's got everything to do with density.
Just think of density as how much mass an object has per unit of volume. You know, how much stuff you have in a given amount of space.
Take this wad of fluff. When I scrunch it into a sad little ball, its mass doesn't change, but its density does. Its density gets higher. That's because I've stuffed the same amount of mass into a smaller amount of space.
Hot things have lower densities because heat causes their molecules to spread farther apart. This causes them to rise. Cold things generally have higher densities because their molecules are packed tightly together. So colder things tend to sink.
Okay, but what does this have to do with the Earth and plate tectonics?
Potentially everything. You see, we know the center of the Earth is its hottest part. Because of convection, the hot rock from deep within the Earth rises up towards the surface. Once it gets there, it cools and sinks back down.
Round and round convection goes, turning that molten rock like a wheel. Scientists believe that the motion of convection currents from within the Earth could be responsible for pushing tectonic plates apart.
Just think of the Earth like a person's face. The planet's facial expressions are constantly changing in response to emotional cues from within. Even though we don't know just how these emotions work, there is no question that they are happening. The surface of the Earth, like a person's face, is always moving, changing, and shifting.
Thanks for watching, peeps.